Hello and welcome everyone. Welcome to STEM Education. I am Syed Wahaj and today we are going to learn physics for IGCSE year 10. So the topic that we are going to deal today is turning effect of forces, turning effect of forces. This is the topic that we are going to deal with today. We actually had a class earlier, and in the last class, we studied about what are forces and how the forces have the turning effect. Okay. So in this current syllabus, we are going to study about rigid bodies. We are going to study about rigid bodies and which are extended rigid bodies. Extended rigid bodies. Okay. So that's what we are going to study today. So what are rigid bodies? Rigid bodies are those bodies which are inflexible. Those bodies which do not undergo any kind of deformation when a force is applied on it. So we have a rubber band. This is a rubber band. This is a rubber band, and this rubber band is non-rigid body. Non-rigid body. Okay. And then we have a piece of wood. This is wood, and this wood is a rigid body. This wood is a rigid body. Okay. Why do we call this wood a rigid body? Because when we apply some force on this wood, it doesn't undergo any kind of deformation. Well, it does sometimes, but mostly we can take a log of wood to be a rigid body. It doesn't undergo deformation, or even if it goes a little bit of deformation, it is really negligible. We can neglect the deformation effect of forces on woods. But on the rubber band, if we apply a little bit of force, it gets extended and it significantly gets deformed. So when we apply two or more forces on a rigid body, which is extended, which is not a point mass, what happens? It may or may not undergo rotation. So let's take a rigid body. We had an example in the last time as well. Let's take a block of wood, and on this block of wood, we can apply force over here and another force over here. So we have 10 Newton force applied at this point A, and then we have 10 Newton force applied on point B. So both point A and B are experiencing forces of 10 newtons each, but these two forces are opposite to each other. Both these forces, let's call this force F1 and let's call this force F2. So these two forces, F1 and F2, are being applied at different points in the body. But when we look at the scenario, we would see that these two forces are acting along the same line. We can say that these two forces are collinear. And when these two forces are collinear, they basically balance each other. And when they balance each other, they do not cause any kind of turning effect. But let's take another case. Let's take this point B somewhere below. Okay, somewhere below. So what is happening over here? We have a block of wood, and on this block of wood, we have two forces, F1 and F2. So these two forces are not actually acting along the same line. The line of forces are different and a little bit displaced from each other. Then we say that these two forces would actually cause this block to rotate. This block would rotate like this. Okay, so these two forces would cause this block to rotate like this. So it was earlier in this position, it will go like this when these two forces of 10 newtons, which are opposite to each other in direction, but they're acting at different points, so that the line of action of these two forces are not the same. So when such a case exists, these two forces would cause the rotation of this block. Got it. Now let us study another topic which is related to the same thing. This thing is all about moment of forces. Moment of forces. Okay. Now let's talk about the idea of moment of a physical quantity. So for understanding moment of force, we have to understand two things. We have to understand the idea of position, position vectors, position vectors, and the idea of multiplication, multiplication of a vector to another vector or scalar. Okay. So today, this is the topic that we are actually going to deal with. We are going to deal with moment of force. I am sure you are not, I have a pretty good idea that you don't really have an idea about vectors and how vectors are treated, what are position vectors, and how do they get multiplied by one another. So this is the whole soul and complete thing that we are going to focus our attention today. Okay. So let's get started with the first concept that we are going to deal with today. And that first concept is going to be about vectors. About vectors. What are vectors? Okay. So have you ever heard about the word vector? You cannot hear what I'm saying. Okay. You cannot listen to what I'm saying. Okay. Let me see how many participants are there. Jahangir sir, are you able to listen to what I'm saying? Am I audible to you, Jahangir sir?
Yeah.
Okay, okay. So Jahangir sir can listen to me, but Talha is somehow not able to listen to what I'm saying.
Talha, okay, let me figure out with him. What's the problem? Talha, can you speak? What's the problem? Okay, he will join again. I think he will join again.
Okay, okay. Let him join again because he's not able to listen to what I'm saying. I guess he's going to join now.
Yes, sir, he will join in some time. No problem, he will join.
Okay.
You can continue, he will join.
So, so vectors, we are going to deal with the idea of vectors. Okay. We know about some physical quantities like energy. Energy is a physical quantity. Energy is a physical quantity. Okay. And then there is another physical quantity known as force. Okay. Then there is a physical quantity known as mass. Another physical quantity known as velocity. Okay. So whenever we are talking about energy, let's say somebody has 5 joules of energy. A person has 5 joules of energy. So it's like a person has some kind of money. Okay. So a person has some kind of money. So we are talking about the idea of money. So if somebody has some money, we can't really have any discussion about the direction of money. Money does not have any direction. Similarly, if something is having some sort of energy, then the energy does not have any kind of direction. Also, this mass, 5 kg, 2 kg, 7 kg, mass of a thing, something which is heavy. So how much mass something has, how much amount of matter a body contains is given by the mass, and it does not have direction. So the idea of energy and the idea of mass does not require the specification of direction. Specification of direction. So energy and mass do not have direction. But whenever I'm talking about force, whenever I'm talking about forces, force or velocity, it has a direction. Okay. So if there's a chair in a classroom, Talha, can you listen to what I'm saying? Am I audible? Am I audible, Talha? Talha, am I audible to you?
Yes.
Okay. Okay, Talha. So I was actually talking about vectors. Have you ever heard the word vector earlier?
Yes.
You know vectors. What is a vector? Can you tell me what is a vector? Can you tell me what is a vector? Talha, any idea? Do you have any idea about the vectors?
I don't sir.
Okay. So whenever we are talking about physical quantities, we have two types of physical quantities. A physical quantity that has some kind of direction to it, and a physical quantity that does not have any direction. For example, energy and mass. Energy and mass do not have any direction. We cannot describe energy or mass along with a direction. But whenever we are talking about force or velocity, it has some sort of direction. If I tell you that go ahead and apply a force of 10 Newton on a chair which is in your room, and tell me what would happen to the chair when you're going to apply a force of 10 Newton on it. Let's see. Let's say this is a ground, and on this ground, I have this chair. Okay, I have this chair. It's on the ground. Somebody tells me that I have to apply a force of 10 Newton on this chair. A force of 10 Newton on this chair. So if I'm going to apply 10 Newton like this, it will stay at its place. But if I'm going to apply 10 Newton force like this, then it may topple. If I'm going to apply 10 Newton force like this, the possibility of it toppling increases. If I apply 10 Newton force over here, it would have a different effect. So force does have direction. Until and unless we specify how much force we are applying on something, we do not have the idea that what is the outcome of the application of force. So something that has a direction is called a vector quantity. Something that has a direction is called a vector quantity. And something that does not have a direction is called a scalar quantity. It's called a scalar quantity. So we have a vector and then we have a scalar. What is vector? Force is a vector quantity, velocity is a vector quantity, and there are many other things like electric field, like magnetic field. There are different kind of things which have an idea of direction applied with them, and those quantities are known as vector quantities. And the things which do not have any directional attribute, these are known as scalar quantities. Okay. Now, how do we work with vectors? So whenever we talk about vectors, we actually draw an arrow like this. So we have this arrow, and this arrow basically has a length, and then it has a directional attribute as well, which is understood by the fact that it has an arrowhead and an arrow tail. This is an arrowhead, and this is an arrow tail. So the length of this arrow, the length of this arrow gives us the idea of the magnitude. Okay. If the arrow is longer, that means the vector has a higher value. If the arrow length is smaller, it means that the vector has a smaller value, that the quantity has a smaller value. And then we have this direction, it gives us the idea of direction, and we usually use angle to represent direction. Okay, let's do one thing. let's draw an x-axis and let's draw a y-axis. Okay, let's draw an x-axis and let's draw a y-axis. So we have these two axes and we have an arrow like this. Okay, we have an arrow like this and we have, let's take another arrow, this one, and let's make it like this. Okay, so these are two different arrows. Both these arrows represent forces. Okay, both of these arrows represent some kind of force. Okay, so both of these arrows, let's call this is force F1 and this is force F2. But we can see that both of these arrows have equal length, but they are having different directions. So if this is, let's say, 10 Newton of force, is it also going to be 10 Newton of force? Right. But the force F1 and the force F2 are equal in magnitude, but they have different directions. Okay. So we represent the force F1 and the force F2 with arrows. This one is for F1 and this one is for F2. Both these arrows are of same length. That means the force has the same value in both these cases. But as we can see that they have different directions. So this is a vector and we use vectors to represent like that. Okay. Now what we do, we try to understand what is the effect of forces when their forces, the forces are not acting at the same point or along the same line. That is the point where we study about the turning action or the turning effect of forces. Okay. So let's draw the x and y axis again. This is a y axis and this is an x axis. Okay. And let us have an extended body like this. This is an extended body. Okay. Let's apply a force like this, and let's apply a force like the same one, but like this. Okay. So this one. Okay. So we have these two forces. Let's say this is the force of 10 Newton here, and then this is the force of 10 Newton here. So both the forces are of same value and they're acting at the same point. So if somebody would try to know that what is going to be the turning effect of these two forces, we would say that both these forces have no turning effect. They have no turning effect. Okay, no turning effect. These two forces are not going to be responsible for this body to turn. Okay, let's do one thing. Let's bring this one to this point. Okay, let's bring this one to this point. So now tell me how much is the turning effect of these two forces. Okay, there would be a kind of rotation like this, right? When it is going to be experience a force like these, two 10 Newton forces which are displaced, then we can have a turning effect like this. Okay, so we have these two forces, and these two forces are causing a turning effect in this pink object. Got it? What if we bring this one nearer? Is it going to have more turning effect or less turning effect? Now it's going to have a lesser turning effect. We bring it very near to each other. Then still we are having lesser and lesser turning effect. So the farther the forces are from each other, the farther they have the distance from each other, the more turning effect they would be having. So what we do, we can make a line like this. This is the line of action of force F1. Let's say this is force F1. And what this line signifies? It signifies the line of action of force F1, right? Also, we can draw like this as well. We can draw like this as well. Okay, and this is the line of action of force F2. Line of action of the force F2. So F1 and F2, we have two forces. Both the forces are of same value, and both the forces are of equal value. And they are opposite to each other, and their lines of actions actually they are displaced from one another. Now what we do, we try to draw a straight line, which is between these 2 points, and let's call the distance d. Okay, so the larger is the value of d, the more turning effect forces F1 and F2 would be having. So if they are nearer to each other, then we would be having lesser turning effects, and when they are farther to each other, then they would be having a greater turning effect. Okay, so let's ask this question: what is a moment of force? What is moment of force? Okay, so a moment of force would be the force multiplied by the distance between lines of actions of both forces, between lines of action of both the forces, That's what the moment of force is all about. Okay. Now let's do an example based on that. Let's do an example based on that. Okay. This is x-axis. This is y-axis. This is a body, and on this body we have 2 points. There's a point A, there's a point B, and then there's a point C. There are three points, and on all these points we have different forces. Let's say the force on B is FB. The force on C is FC. And the force on A is FA. Right? Now we want to know what would be the turning effect of all these three forces. What would be the turning effect of all these three forces? Okay. So what we try to do here is that we take the turning effect of these forces about origin. We ask the question, what is the turning effect of all these forces? The turning effect of all these forces about origin. Okay, that is the question. Now we have this question. We have a body, the yellow body, and this yellow body is made up of 3 points: point A, point B, and point C. And on these 3 points, we have 3 forces. The force on B is acting like this, the force on C is acting like this, and the force on A is acting like this. Now we want to know what is the turning effect of all the 3 forces combined for this body, taking O as the origin. O is the origin. Okay. Now let's try to do this question. Let's try to find out what's going to be the answer of this question. So when we are actually trying to do turning effect of forces, we want to find out the moment of force. We want to find out the moment of force. Now let's do one thing. Let's remove everything else. Let's remove all these things from here and just focus on A, right? Just focus on A. So this is the force, and let's draw line of action of this force. This is the line of action of this force. Okay. Now we want to understand the turning effect of this force, the turning effect of this force about origin. So what we do now, we would draw a line from O perpendicular to this line, perpendicular to the line of action, and let's call it D1. Okay. Let's say the F1 force. Let's write it down the value. Let's say F1 force is 10 Newton, and FC force is, let's say, 5 Newton, and FB force is, let's say, 7 Newton. We measure forces in newtons, so it is 7 Newton. So we have a body, the yellow body, and this body has 3 points, A, B, C, and all these 3 points, they are experiencing 3 forces, FA, FB, and FC. The force FA is 10 newtons, the force FB is 7 newtons, the force FC is 5 newtons, and it is being exerted like this. Okay. Now we have to find out the turning effect of these forces about origin O. Okay, this is the question. Let's read this question again. What is the turning effect of all these forces about origin, about the point O? So we will deal with each and every point accordingly. Okay, separately. First, we are going to take the FA force, and then we are trying to find the value D1. Okay. So what is the turning effect of F1 force? Let's write down. First, it is turning effect of force F1. Okay. So in order to understand the turning effect, what we do, we imagine a rod like this. We imagine a rod like this. And we imagine that we have pinned it down at the origin, and we are applying the force Fa. What would the force Fa? What would the force Fa do to this green rod? Okay. What would this force Fa would do to the green rod if I'm holding this green rod at the origin in our fingers? Okay. What would this do? Okay. This is the question. So this Fa force would bring this one down, and it would make this rod rotate clockwise. Okay. So what is the turning effect of force F1? It would cause rotation clockwise. It would cause rotation clockwise. Okay. And clockwise rotation is known as negative rotation. Clockwise rotation is known as negative rotation. Okay. And how much would the turning effect would be? The turning effect would be having a value of force into this distance d1. Okay, let's say this d1 is 2. The value of d1 is 2. Okay, so the value of turning effect, value of turning effect of force F1 is equal to force F1 multiplied by perpendicular distance from O to the line of action of force F1. Okay, what does it mean? And this is known as torque. This is known as torque due to force F1. Okay, F1 or FA, rather we call it FA. Okay, torque due to force FA, right? Let's write it down, FA, right? Everything. Torque due to force FA would be the force FA. What is the force of FA here? We have 10 newtons. 10 newtons multiplied by what is the distance between origin and the perpendicular distance from origin to the line of action of this force, this line. So what we do, we start from O and we draw a perpendicular from O to this line, and this distance is 2. So it is into 2 meter, and this is going to be negative. Why negative? Because this force is causing this imaginary rod to rotate clockwise, and clockwise rotation is a negative rotation. So we can say that the torque due to force FA would be negative 20 Newton meter. Negative 20 Newton meter. That is the turning effect of force FA, right? I think now you have understood. What was the question? The question was, we were having a block, a body, which is extended body, and it is a rigid body. And on this rigid body, we have 3 points, point A, point B, and point C. And on these 3 points, we have 3 forces, FA, FB, and FC. The force FA is of 10 newtons, and it's going downwards. And the FB is in this direction, and FC is in this direction. So the question is, what is the turning effect of all these forces on this body? And we have to also specify about which point we are trying to find out the turning effect. So here it is given that we have to find the turning effect about the origin. Okay, so we take this origin, and in order to imagine the turning effect of the forces, what we would do, we would imagine a rod that goes from O to the point A, where the force FA is acting. And we would imagine that if we are going to hold this green rod at O in our fingers and then apply the force FA, what would be the turning effects of force FA on this green rod, which is an imaginary rod? So we would see that the imaginary rod would turn clockwise, okay, would turn clockwise. So a clockwise rotation is a negative rotation by convention. We call it a negative rotation, and when we have an anti-clockwise rotation, we call it a positive rotation. So we see that this green rod would undergo a negative rotation under the influence of force FA. Now, how much would be the value of turning effect? The value of turning effect would be the product of the force, the amount of force, and the distance between the line of action of force and the origin O, about which we are trying to find out the turning effect. So what we do, we draw a perpendicular line. This red line is a perpendicular from O to the line of action of force Fa. Let's say this distance is d1 and d1 has a value of 2. So what we do, we multiply the 2, which is the distance from O to this line, perpendicular distance, and we multiply this 2 to this Fa. And we give it a sign of negative, a negative sign. Why so? Because it is causing a clockwise rotation, and a clockwise rotation is known as a negative rotation. So the turning effect of force Fa, and in other words, we can say the torque due to Fa would be 10 Newton into 2 meters with a negative sign. That would be a negative 20 Newton meter. That would be the turning effect of force Fa. Got it? Talha, did you got this thing? Did you get this idea what turning effect of force Fa is? Have you got it?
Yes, sir.
Talha, you understood it? Okay.
Yes, sir.
So how many forces we have here? We have 3 forces, and out of these 3 forces, we have what? We have the turning effect for Fa. Okay. Now let's take the second case. Let's take the second case. Okay. Let's take the second case. Let's put it here. Okay, let's put it here. Got it? Now let's get ourselves concerned with the force Fc. Okay, let's get ourselves concerned with the force Fc. So let's delete it altogether. Let's delete it. Let's remove it. Okay. Let's remove it. Okay. So we are going to get ourselves concerned with the force Fc. Fc. Okay. Fc. Let's delete everything. Let's have an idea about Fc. Okay. Now we are trying to find out the turning effect of force Fc. The turning effect of force Fc. Turning
Sir,
effect.
what chapter is this?
Turning effect of forces.
No, like what number chapter? What chapter number?
The chapter number is, let me see, what is the chapter number? Hold on for a second. Fourth, chapter number 4. Okay, you got it? You got it?
Yes, sir.
So the 4th chapter is the turning effect of force. Now we have to find the turning effect of force Fc. Turning effect of force Fc. Or in other words, the turning effect of force, the whole of this thing can be said as torque. Torque due to Fc. Okay. So now what we have to do? We have to imagine a rod. We have to imagine a rod which starts at O and which goes up to C. Okay. This is the rod that we are having. Okay. Since we have to take the turning effect about the point O, we have to hold this rod at C. And then we have to apply the force Fc on this rod. Tell me, Talha, what would happen to this rod if we will apply the force Fc on this rod? What will happen? And if we are going to hold it at point O, what would happen?
Sir, can you repeat the question?
We have this green rod, you can see?
Yes.
We have imagined green rod. And at point C, a force of 5 Newton is applied as shown in the direction, as shown in the figure, right?
Yeah.
We are holding this green rod at point O with our fingers, okay? What would this force do to this rod? That is the question.
It would make it move anti-clockwise.
Yes, it would make it move anti-clockwise. So is anti-clockwise positive rotation or a negative rotation?
Positive.
It is a positive rotation, okay? And what do we have to find out here? We have to find out torque due to force Fc, a turning effect of force Fc. That's what we have to find out, right?
Yes.
What next we have to do? Do we have to make a straight line like this? We have to make a straight line like this or not, right?
Yes.
What is the name of this line? This line is called line of action of force Fc, right?
Yes.
Okay. And what we do next? We draw a perpendicular from O to this line. Like this is the perpendicular that we have to draw, okay? And we have to find out the distance of this line. Let's say the distance of this line is 5 meters, okay? Right? So what would be the turning effect of force Fc? Can you tell me? Or let's call it 4 rather than 5. Let's call it 4 meters. 4 meters, okay? Okay, what would be the turning effect of force Fc? It would be the product of force and this distance. Got it? What would be the distance? 4 meters. Okay, 4 meters. And we would multiply it by 5 meters. Correct? Got it?
Yes.
So how much would be the turning effect of this force? How much would be the turning effect of this force? 20. 20 what? 20 Newton meter, right?
Yes.
Positive or negative?
Positive.
Why positive? Why do we have positive here?
Because it's rotating anti-clockwise and it's positive.
Exactly. It is rotating anti-clockwise. Got it? Now you're understanding the rotational effect, the turning effect of forces?
Yes, sir.
Okay. Okay. So how many forces in total we had? How many forces we had earlier? Tell me.
We had 3.
We had 3 forces. What were the names of these forces?
FA, FB, and
FA,
FC.
FA, FB, and FC, right? Okay.
Yes.
This is what we were having. Okay. So in order to find out the turning effect of force Fa, we found out that the value of Fa is 10 and this distance is 2 and it is making this rotate clockwise. So we said that the turning effect of force Fa would be negative 20 Newton meter. The turning effect of force Fc would be positive 20 Newton meter, right?
Yes.
Right? Okay. Now let's find out about this force. This force, about this force, this force. Okay. Now we are having one force remaining. Okay. Okay. Got it?
Yes.
Let's delete all other forces and let FB remain. Okay. Oh. Now what do we have to do here? Tell me. Tell me, keep telling me. What do we have to do now? What should we do now? What is the first thing that we should do in order to find out the turning effect of force FB? The first thing we should do is that we should imagine a rod like this. Okay? This is the first thing that we have to do. We have to imagine a rod like this. Okay? That starts at O and ends at B. Okay? And then we have to think how much turning effect this FB would be having on this green rod and what kind of turning effect it would be having. So tell me, what would this force FB do to this rod if we are going to hold it at origin from our fingers, with our fingers? What would it do?
It's gonna rotate clockwise.
It's
That's
going to
negative.
rotate clockwise. So the turning effect is positive or negative?
Negative.
It's a negative, right? Okay. After this, what should we do now? Should we draw a line like this? Should we draw a line like this?
Yes.
What is the name of this line?
The line of action.
Line of action of force FB. This is known as line of action of force FB, right? Okay. Now we have to draw a perpendicular from this point to this point, right? We have to draw a perpendicular line. Okay. Let's say that this distance is 3 meters. Okay. So what would be the torque? What would be the torque due to FB? What would be the torque due to FB? Can you tell me?
Do you want me
Can
to
you tell me
tell you the answer if I multiply seven? Yeah, okay, wait.
Okay, tell me what would be the turning effect? Torque.
So what does it say on the yellow line?
Yellow line, this value.
Yeah.
This value is 3 meters.
It's gonna be minus 21 Newton meter.
Very good. This would be minus 21 Newton meter, right? Okay. Now you understood? Now you understood the turning effect of all the 3 forces individually? Okay. Now let's try to find out the turning effect of all the forces. The turning effect of all the forces. Okay. Turning effect of all the forces. Turning effect of all the forces combined. Okay. So what do? We write it torque due to A, torque due to FA, plus torque due to FB, plus torque due to FC. That's what we would have to write. We would have to add up all the 3 effects, right, to have the total effect. What is torque due to FA? Is it negative 20 Newton meter, right? So torque due to FA would be minus of 20 Newton meter. Torque due to FB would be negative of 21 Newton meter. 21 Newton meter. Okay. Negative 21 Newton meter. Plus what would be the torque due to Fc? It's going to be a plus 20 Newton meter. So let's add all of them together. After adding all of them together, we have this negative 20 Newton meter and this positive 20 Newton meter. They would cancel each other, and finally we will be left with a negative of 21 Newton meter. And that is going to be the answer to this question. That is going to be the turning effect of all the three forces on this body. Okay. Got it?
Yes.
Oh. So do you want to write it down? Do you want to write it down, the whole question?
Yes, sir.
Go ahead, write it down. I'm giving you a few moments. Go ahead, write it down. This is the question. And here you go. Okay, done?
Not yet, sir.
Okay, done?
No.
Okay. I think you're done with the writing thing.
Almost.
Okay. Done.
Yes.
Okay. Now, the next thing that we have to understand is that same force, the same amount of force can have different torques. Let's try to understand this idea. So let's do one thing. Can you tell me what is it that I have drawn here? What is this drawing of? What is this? Tell me. What
A
is
door.
this? This is a
Sorry.
door, right?
Yeah.
Yes. So this is a door. Okay. We want to shut this door down. It's an open door, right? The door is open, it's not closed. Okay.
Yes.
So what we can do, we can push this door at this location, right? Let's
Yes.
say we are applying a 10 Newton force on this door, which is, and the door handle is 1.5 meters away. Okay. Okay. So what would happen? The door would go like this, anti-clockwise, right?
Yes. It would close.
Okay. So can you tell me what would be the turning effect of this 10 Newton force here?
Anti-clockwise.
Yes, it's anti-clockwise, so it is negative or positive?
It's gonna be positive.
It's gonna be positive. And how much would be the turning effect? How much would be the torque value? How much would be the value of it?
15 Newton meter.
15 Newton meter. Positive 15 Newton. Positive 15 Newton meter. That is going to be the torque if handle is here. Okay, now let's do one thing. Let's bring this one a little bit closer. Okay. Now the handle is not at the edge of this one. It is going to be 1.2 meter, right? Earlier it was 1.5 meters. Now we have brought this door handle closer to this axis, closer to the axis about which it is going to protect. Okay, we have brought it closer to this axis. It's now 1.2 meters only. What is the torque now?
Positive 12 Newton meter.
Positive 12 Newton meter, right? So if we keep moving towards the axis of rotation, this is called the axis of rotation. If we keep moving towards the axis of rotation, don't you think the turning effect would keep on decreasing?
Yes, it will continue
Yes,
decreasing.
right? It will keep on decreasing, right? Also, just tell me what would happen if rather than pushing the door, we are pulling the door. What would happen? If 10 Newton, we are pulling the door with 10 Newton force, what would be the torque now?
Negative 12 Newton meter.
Yes, it would be negative 12 Newton meter. So now you understand that same force can cause different torque depending on what is the distance of that torque from the axis. Or the axis, we have another word for the axis, and that word is fulcrum. This can be known as fulcrum, right? It is fulcrum. Got it?
Yes.
It is fulcrum. Now you understand we can have a turning effect which would be dependent on the force as well as this distance. Okay. Okay. Now, have you ever visited a nursery where we have seesaw? Torque on a seesaw. Torque on a seesaw. Okay, let's make a seesaw. Okay, have you seen a seesaw? It's like
Yes,
this.
sir, I have.
It's like this, and on this seesaw we have this. This is a seat where somebody can sit, and then there is a seat where somebody can sit, and here we have a handle here, and we have a handle here. So we know this is called a seesaw, right?
Yes, sir.
Okay. Now, what do we call this point? What is this point known as? This point is known as fulcrum, right? Why?
Yes, sir.
Because there would be turning about this point. The whole thing would be turning about this point. This is the point which will not move. What is a fulcrum? Fulcrum is the point on a rotating body, the point on a rotating body that does not move. That does not move is known as fulcrum. Right? The point on a rotating body that does not move is known as fulcrum. So on this seesaw, you can see that this point is not moving at all. It is going to be on its own position. Okay? This may go up or down, this may go up or down, but this point will not move at all. So that is why we call this a fulcrum. Just go ahead and write that down. Write the definition of fulcrum. This is what we call as fulcrum. Okay? Go ahead, write it down. Draw this diagram.
Yes, I'm going to write it now.
Okay. Okay. Now let's do one thing. Have you written it down?
Yes.
Okay. Now, tell me, if it is in just the middle of it, and we apply 10 Newton to this side and 10 Newton to this side, what would happen?
It would stay the same.
It would stay the same. Why? Because the turning effect of the force F1 and the turning effect of force F2 would cancel each other, right?
Yes.
So this F1, what would this F1 try to do? It will try to make it go clockwise, right? Correct?
Yes,
And
sir.
this would try to make it go anti-clockwise. Okay? Got it?
Yes, sir.
So what we can do, what would be the net torque on this body? The net torque or net turning effect of all the forces would be 0. Got it? The net torque or the net turning effect of all the forces would be 0. Okay? Right?
Sorry, can you repeat that again?
Okay. How many forces are there? 2 forces? The force F1
Yes, 2
and the
forces.
force F2. Okay? The force F1 is trying to make it go clockwise, and the force F2 is trying to make it go anti-clockwise. Both the forces are equal, and both the distances are equal. So the turning effect due to F1 and the turning effect due to F2 are equal, but they are opposite. One is clockwise and one is anti-clockwise. Okay? So we can say the turning effect torque tau due to F1 is how much? Let's say it is 2 meters. Okay? How much tau F1 would be? It would be negative 2 into 10 on minus 20 Newton meter. Okay? And what
Yes.
would be the torque due to F2? It would be positive 2 into 10. It would be plus 20 Newton meter. Okay? If we add it up, the net value of torque, that would be tau due to F1 and then torque due to F2. That would add up to be positive negative 20 Newton meter, negative 20 Newton meter with positive 20 Newton meter, and which would make it 0. That would be a total 0 turning effect or 0 torque. Got it?
Yes, sir.
Okay. So we can do another thing. Let's do another thing. Instead of applying 10 Newton here, let's change it a little bit. Let's change it a little bit. Let's bring it a little closer. Okay? Let's bring it a little closer. Let's bring it at 1 meter. 1 meter. Okay? Got it?
Yes, sir.
Let's bring it at 1 meter. And instead of applying 10 Newton force, let's apply 20 Newton force. 20 Newton force. Yeah. So now, what is the value of F1?
20 Newton.
20 Newton. And what is the value of F2?
10 Newton.
How much is the distance of F1 from the fulcrum?
It was 2 meters, but then it's now 1 meter.
1 meter. Okay. And what is the distance of force F2 from the fulcrum?
2 meters.
2 meters, as it was earlier. We didn't change it at all. Okay. Now tell me, we have not changed the turning effect of force F2, right? Tell me what is the turning effect of force F1 is now. Okay, tell me, what is the turning effect of force F1 now?
I think it's going to stay the same because
Yes, it's going to stay the same because we have to multiply 20 by 1. That will remain the same, 20. Okay? Now,
yes, sir.
we can say that in this condition, these two forces are balancing each other, right?
Yes, sir.
So, in this condition, we can say a lighter object can balance a heavier object. Okay? A lighter object, okay? A lighter object can do what? A lighter object can balance a heavier object, right? A heavier object. If the lighter object is farther from the fulcrum. Can we say that?
Yes, we can, sir.
We can understand that the F1 is like a heavier person is sitting at this position and a lighter person is sitting at this position. But a heavier person can be lifted by a lighter person. Just the lighter person has to sit farther, more distant from the fulcrum. Got it? You got this idea?
Yes, sir. I got it.
You got it. Good. So this phenomena can be used to lift heavy weights using lesser force. Okay. So the above idea or principle can be used to lift heavier objects using small forces. Got it?
Yes.
Okay. For example, we can take a rod like this, okay, and on this rod we can put a stone like this. Okay, let's put a stone like this. So putting a stone like this makes this point as what? What is this point?
It's the fulcrum.
Fulcrum, right? And we can put a heavy load at this end. We can put a heavy load at this end. Heavy load. And we can apply a small force at this end. Small force at this end. Okay. So this distance is d1 and this distance is d2. Okay. Okay.
Yes.
So let's call this as heavy load L. And let's call it a small force F. So if this F force is going to balance this heavy load L, then we can say that force F multiplied by D2 is equal to heavy load L multiplied by D1. Got it?
Yes, sir.
And then we can use this principle to lift very heavy load by applying a little force at this end so that we have a longer distance on this side. Okay, got it?
Yes.
So this is the idea, this is the turning effect of forces, and this is a very, very important and a very effective method to increase our capacity to lift things, to manage to transport one thing from one place to another. You might have seen different trolleys, and with wheels, we can put little load at one end of the trolley and we can lift heavy loads. Okay, have you seen that? Have you seen trolleys like that? Trolleys like that, or like
Yeah, sir.
such trolleys where we have this wheels at this end, and we can fill a lot of water like this, and we can put a little water or sand or whatever. We can put a little load over here, little force over here, and we can lift this thing, and we can bring it from one place to another. We can carry it, right? Like briefcase. Also, we have briefcase, right? We have traveling bags. We have traveling bags like this. Okay, on this here it is the wheel, and here it is the handle. So this handle is pushed like this, and we can lift it like that. Okay. So all these things are based on this principle of turning effect of forces. Got it?
Yes.
So is everything clear to you? Is there any point where you would want me to recapitulate or to delve a little bit deeper on this topic? I think you must have understood each and every point, how forces are applied, what is a positive torque, what is the negative torque, and what does it mean to have the total torque on a body. I think everything is clear to you.
Yes, sir. Everything's clear.
Okay.
I understood everything.
Okay. Good. So I think we are going to have our class done, and we'll meet in the next class and we'll discuss further. We'll do some questions that are asked in the examination, and we'll start from there. Okay.
Okay, sir. Bye.
Okay. Goodbye. Thank you so much for joining us. Thanks so much.